Welcome to our second of our Nano Explorations student talk series. It's a way to keep our students engaged with you as they do the continued work in their homes and their dorm rooms in this unique and unusual time. So my name is Brian Anthony. I'm one of Robin's advisors, also Associate Director of MIT.nano. I'll moderate for today, which really means my job is to introduce Robin and field the questions and direct them to him afterwards. For coordination, please type your messages, or if you have a question, please indicate in the chat or raise your hand, and we'll, at the end, have Robin answer those questions as time allows. Robin Singh is a doctoral student in the Department of Mechanical Engineering. He's been phenomenally innovative in developing uses for integrated photonics in a number of different medical applications. And today he's going to share his work on-chip biophotonic particle and gas sensors for a number of applications, which, as you'll potentially imagine, has some really interesting opportunities given our current situation with COVID. Robin, thank you for preparing for today, and I'll turn it over to you. And actually, I just got a message. We are recording Robin. And we will also be recording your voice if you ask questions. So we'll be recording Robin and his slides as he goes, and then anything that is said during the session.
All right. Thanks so much, Brian, for introducing me, and hello, everyone. Welcome to the MIT Nano Explorations Student Seminar Series. And I'm going to present my work. So let me share my slide here. All right, so my name is Robin Singh, and I'm a final year PhD student in the Department of Mechanical Engineering, and I'm advised between Dr. Brian Anthony and Dr. Anu Agrawal. And today I'm going to share my work on-chip biophotonic particle and gas sensors, ensuring a safe environment indoors and outdoors. Motivating the topic in general about the photonics that are being used in healthcare and biomedical applications. So as we know, it is being used in varieties of applications, be it on microscopy or laser therapies or imaging, or that for that matter, if you perform spectroscopy. And if we can find a way to miniaturize these optical components on a chip, it is possible to provide these solutions in the hands of doctors and patients at point of care. So looking to miniaturize these, we explored the realm of integrated photonics. Photonic integrated circuits have been around in industries for more than a decade now, and they're used by communication industries for improved bandwidth and precise signal processing applications. But just to get an understanding of what these photonic integrated circuits are, let's compare them with conventional electronics that we see almost everywhere in our electronic gadgets today. So electronics is more about electrons in motion, and they have the building blocks such as voltage supply, transistors, resistors that are working together to perform a fundamental operation. On a parallel paradigm, we have photonics that consists of photons in motion with the building blocks such as waveguide, laser source, detectors, modulators, working together to do the equivalent fundamental operations. So with this idea, it is now possible to miniaturize whatever we have the bench scale optics. For instance, if we have a bench scale optics in an equipment that has a laser light source, the beam splitter, the bender, and a photodetector, it's always possible to find an equivalent on-chip PIC component. For example, we can completely replace the system with a semiconductor laser diode. We can use waveguides to modulate the light, and then we can use the photodetector that is patterned on the device itself to detect the optical signal. So this is a really good way of miniaturizing any optical components that we use for various sensing applications. And further, because we are seeing these PICs for biosensing applications for today's talk, I'm going to refer them as biopics in my talk. So coming to our point of interest, that is aerosols and gases. So by definition, aerosols are about the particles that are either solid or liquid suspended in the gas medium. And they are very crucial in a number of applications, or it could be for a biohazard or weapon that we all are familiar with the pandemic scenario going on right now. And this has more in the nano level particles such as viruses or bacteria, ranging in the dimensions from 1 nanometer to about 200 nanometers. And then it could be in terms of air pollutants and soot particle, which is emitted by chimneys in factories and industries. And these pollutants are majorly consisting of micron-sized particulate matter ranging from about hundreds of nanometer to as big as 500 micron. And then, more importantly, they are also very crucial for pulmonary drug delivery. So we have seen like there's a lot of application of these aerosols or pharmaceutical particles that are used for pulmonary drug delivery application through nebulizers or inhalers. And these are again some micron-sized particles ranging from about 0.1 micron to about 5 micron. So with these applications in our mind, we are looking for getting these biopics for sensing aerosols. And our today's focal point of discussion would be divided into points. The first point would be for these biopics to sense or characterize nano or micron particle in air. And the second focal point would be these biopics to develop an on-chip detection to detect a virus genome.
你做那个面包不太实际。
Sorry. All right. So yeah. So
just to interject there for a moment, if you're not, please, if you can mute your microphone if you're not speaking, please. Thank you.
Okay. Thanks. So yeah. So coming to our first topical interest, that is biopics for nano or micron particle characterization in air. Let's see when I say characterization of aerosols, what do I actually mean is it could be chemical characterization where we are estimating the chemistry of the particles, that is understanding the chemical nature or the bonds that are present in the particles. And the people that they are conventionally trying to do this is using a spectroscopic method like Raman or FTIR spectroscopy, or it could be a fluorescent particle imaging or a mass spectrometer. And similarly, we have physical characterization that refers to more estimating the particle size and count. That is, in a dispersion, how many particles are present or what's the distribution of these particle size. And the way people do currently is by using a bench scale optical method where they have a light source and they understand the scattering pattern of a dispersion of aerosol that is being passed through this light path. Or they use other methods where they try to understand the motion of a particle in electric field and see how it changes its direction based on the size of the particle. However, a close look to these conventional methods would show you that these are pretty bulky setups. They are expensive, and it's really tough to deploy them for field testing or to integrate them with miniaturized sensing systems. And the most importantly that I want to highlight here is it cannot provide the complete characterization. When I say the complete characterization, I mean there's no framework that provides physical characterization and chemical characterization both on the same chip. So the question that we ask is, can we develop an on-chip method to provide combined framework for physio-chemical characterization? So working on this, we are using these biopics to perform on-chip aerosol spectroscopy in near IR and mid IR range using microstructures such as microring resonators or spiral waveguides. Let's first understand what are these ring resonators to just very quickly see what they do, and then how do we use these ring resonators to sense the aerosol particles. So essentially the idea of ring resonator here is you have a bus waveguide pattern on your device, and then you have a very close cavity, very close to this waveguide. And as you couple light to the bus waveguide, for a particular wavelength of your light, it interferes with this cavity constructively and results in a dip in your transmission pattern and output. So you would see a dip for that particular wavelength. So now if there are particles that are coming in the vicinity of these kind of ring resonators, it perturbs the cavity, and this perturbation is manifested in two forms. The first form is in the terms of shift in resonant peak, meaning the peak or the central wavelength of your resonance shifts either right or towards the left. And if we see a little bit more math into this, this change in peak is a strong function of the radius of the particle that is interacting with your resonant cavity, as well as the effective index of the particle. So this is more to do with particle size and count. And the second effect that is seen in this perturbation is the change in quality factor. And this change in quality factor changes the peak sharpening effects, and this is majorly because of the insertion losses that happen when there's a particle interacting with this cavity. And they are traced back to the absorption coefficient or the kind of chemistry or the chemical nature of the particles. So the first effect I mentioned could be used to help to get the estimation for size and count. And the second effect could be used to understand the chemical identification of aerosols. So with this working principle, we design our sensor module. So we have this housing of the sensor module that has a biopic design consisting of a tunable light source, either on a chip or off chip, that couples light to our bus waveguide. And then this light is dispersed to individual set of ring resonators and spirals through directional couplers. And the output of these ring resonators are sensed using the photodetectors that are patterned on the device itself. So to summarize, this biopic has following components. So it has a laser diode, bus waveguide, couplers, photodiodes, and ring resonators, and some back-end signal processing to understand the change in pattern as we see as it interacts with aerosols. Something that I want to make it clear is, so these are the near IR based designs operating between 1500 nanometer to about 1600 nanometer in wavelength, and they are based on silicon nitride photonics. So with these and another crucial design that we have in these biopics is the set of these ring resonators. So the major thing about these ring resonators is, like, we have designed in a way that they have different extent of evanescent tail around them, meaning we have designed these waveguides so that they have different confinement factors. So meaning now you have E1, which is the largest, and for the ring resonator 3, you have the evanescent tail E3, which would be the smallest. So now as a given particle size interacts with this in the vicinity, it is going to undergo a very unique particle light interaction. And this information would be used, it is very useful to retrieve back what's the particle size, count, and what's the chemistry that I would show you in the coming slides. So let's now talk about retrieving the chemical characteristics of aerosol particles using these biopics. So as I mentioned, we have these set of ring resonators, and they have the transmission pattern that changes based on the resonance. So here are the experiments that we performed with our sensor module. So what you see here is we have an aerosol chamber. We pump in aerosol into this chamber, and then the device is sitting right underneath, and we couple in light externally in the transverse direction. And for this test case, we have used some N-methylene aniline based aerosol particles. And what you see here on the graph is the transmission pattern before exposure shown with the blue, and after 1/22nd exposure of aerosols with the red. And the idea here to retrieve the chemistry of particle is to understand the change in quality factor of these peaks. For instance, let's understand this peak 1, which is somewhere around 1535 nanometers or 1532 nanometers. And you can see that with the exposure to aerosol, the quality factor has changed. And then if we take another instance, for example, P2, we can again see there's some sort of, the quality factor hasn't changed much, but there is some change. So meaning the quality factor is changing based on how much that particle is absorbing at that particular wavelength. So if we do this kind of relative quality factor change analysis over this entire range from 1530 to 1610 nanometer, it is possible to have a qualitative absorption spectrum of these aerosol medium. So this is what we get when we do it for individual peak over this given range. And in order to understand how close we are with the ground truth, we compare them with our commercial spectrometer readings. And then we see here that we are able to match the peak nature qualitatively, meaning it's able to give us information on what kind of bonds are present in your aerosol, or like what kind of chemistry that we are dealing with here. And this itself is a very crucial information when you are dealing with such a dynamic aerosol-like medium, which is changing all the time. So this was more about like understanding, okay, being able to get some chemistry information of the particle. Now let's come to retrieving the physical characteristics of these aerosol particles. So as I mentioned, the physical characterization is all about particle sizing and counting, meaning to understand what's the size range and how many of them are present. And in order to do so, again, we get back to our sensor module that has, as I mentioned, it has a chamber sitting right on top of our biopic. And we understand the flow of these particles using some of the computational fluid dynamic based modules to trace the particles. For instance, so if we have a given flow rate of particle, we try to understand the dispersion of these aerosols in the medium in the steady state. And then we try to see for a given flow rate, how many of these particles get into the vicinity of these waveguides. And so this kind of understanding helps us to know, okay, if we have 10 particles that are interacting with our waveguide, what does that mean in terms of the flow rate of particle through our chamber? So this allows us to calibrate this entire sensor module here. And from there, as I mentioned you earlier, to understand the size and counting, we rely more on the peak shift and not much on the quality factor change. And in order to do so, we try to see what's the peak shift for different particle size and the number. For example, for a particle size of about 400 nanometer in radius, and two of them, what kind of peak shift that we see. So these are kind of the color maps that show these peak shift fingerprint for different size and count of particle. And the same thing happens for a different ring resonator design. And this is different from the one that we saw in the ring resonator 1. And the same thing for the 2, for the 3. And the good thing is these all are very unique, and this information is very useful for us to calibrate our sensor so that based on the peak shift response of individual ring resonators, it is possible to say, okay, what's the flow rate or how many particles are there in this entire medium. So with this information, it is now also possible to use the same platform that we use to understand the chemistry of particle to now get the physical characteristics of size and count as well. So, so far, just to know that we are on the same page, what we have seen so far. So we have seen our biopic design for complete on-chip physio-chemical characterization of aerosol particles. Then I established the ability of retrieving the chemical spectrum of aerosols for transmission spectrum. And then we developed framework for understanding the sizing and counting by using some of the simulation models, as well as by understanding the color maps or the shift map that to say. Something very important that I would like to highlight here is because we are using a multiplex system of ring resonators on our sensor modules, it is possible to now overcome the conventional limitation of sensing micron-sized particles. So there was some research that had been done to just sense nano-sized particles with a ring resonator, but they were not able to precisely monitor the micron-sized particles because they were much bigger than the size of a waveguide. But given that now we have multiple of these ring resonators and trying to kind of little bit hijack the way we are post-processing this data, it is now possible to even reach the micron-sized particles as well. So far I was discussing more of these biopics that were operating in near IR range, and that's great. Near IR photonics is very, very well known in the entire communication industries, and something that a lot of people have been researching on. But more excitingly, if we can have these biopics, particularly for sensing application in mid-IR range, it could be of a lot more application. And the reason I say so is, here what I show you are these absorption of different kind of organic molecules. And as you can see that most of these organic molecules have their absorption spectrum in the range of about 2.5 micron to 7 micron. So now if you can develop these biopics operating in this range of about 3 to 7 microns, then we can target a lot more applications that could be relevant for industry, safety, security, environment, healthcare, or transportation. Our focus more today being in the healthcare applications in sensing these particles. And in order to do so, we are using a chalcogenide glass-based photonics, which is very well developed in our MIT through Microphotonics Center. And we are using these chalcogenide glass-based material to develop these equivalent biopics. So here again, our sensor module that we are trying to test right now in a mid-IR range has a spiral waveguide. And then this sensor module also has an on-chip detector. And we have tested these sensors for 2 test cases. The first test case was again for aniline-based aerosol particle sensing, and to understand if we are able to retrieve the chemical spectrum of these particles using these chips. And yeah, so this is what we get from our sensor and what we see from our NIST library plots. And then we also tested with our fellow grad student, Peter, on sensing the methane gas. And here again, we can see that we are very easily able to capture the absorption spectrum around 3.3 micron of methane. So this definitely has a lot of potential to sense aerosol or gas of different organic compositions as well. So this was more about the work that I was talking in sensing nano and micron particle in air. So let's come to our second point of interest, that is understanding the biopics for fluorescent detection of virus genomes. And this could be very interesting given that we are living in a scenario where we want to do a lot more research and understand what could be the better diagnostic tool for virus or COVID-19 equivalent particles. And then to motivate this topic of interest, let's understand the case study of COVID-19 diagnosis. And currently the state of art that people have been trying to use is the molecular diagnostic technique, which was recently approved by FDA about a few days ago. And the idea here of this technique is you have this RNA-based virus, the COVID-19 is an RNA-based virus, and you have a chemical release of RNA or the gene molecules from the virus, and then we try to recognize the pathogen genome in this entire RNA molecule, and then once we've identified these pathogen genome, we replicate it so that we can detect it through our sensors, and then once we replicate it, we attach the fluorescence to these genomes, and then they are tested with a lab-based fluorescent microscope. Of course, because it's a molecular technique, it's really specific, but we also don't want to compromise with the sensitivity of these sensors so that we have as good as performance of the sensor as we want. So currently the bottleneck of the situation in most of the developing nations where they are trying to work out with this is they use the lab-based fluorescent microscopic techniques that would take up to about 4 to 12 hours to return back to the results. And at times it can also result in, it needs some additional sample preparation, and that makes it laborious. So now our idea is if we could miniaturize this entire fluorescent detection to something at point of care, it is now possible to reduce the cost of testing, and that would make it scalable. It would be easily accessible by different communities in the outskirts, and then the sample preparation is much simpler than the one that is used in the wet bench tests. And then if we can come up with a technology that doesn't compromise too much with the sensitivity, with the reduced form factor, that would be of really great interest. So working on this miniaturized fluoroscope, we are again developing a biopic that can take care of that. And the idea of using these biopic here is we are combining our biopics now with microfluidics to develop an optofluidic chip that miniaturizes your light excitation source and the detection source all on the surface of the device. And then that allows us to probe any analyte that is flowing through the microfluidic channel on the top. So digging a little bit deeper into this photonic chip design, the idea here is we are using our photonic chip design that uses a waveguide that couples light from a light source, and then this waveguide terminates with a meta surface, and this meta surface is something that diffracts the light off the plane to illuminate your sample, and then the illumination results in fluorescent signal, and this fluorescent signal is then received by other set of grating or the meta gratings that couple in light and pass it to the photodetector. So this essentially has two ports. The port one is the light excitation port, as I mentioned, that has a meta structure to collimate the light. And once you have the fluorescent signal generated from this, we capture this through the meta surface that are optimized for dipole radiation detection, meaning if you have the light being generated at this point, these surfaces are able to absorb that light and then couple it to a detector. So something as miniaturized as this technology could provide us a scalable technology for point of care fluorescent detection. Further, it could be very low cost, something that we can produce in our foundries and then just use it for molecular diagnosis of various bacteria, be it COVID-19. And then because it's a very localized excitation detection, we are having very low ambient noises in our fluorescent signal. And the other important thing is because the footprint of the entire system is very low, it is possible to multiplex these sensor modules for high throughput detection. So that was a lot more about what I was here to present, but just to motivate the idea of using these integrated photonic platform for more than just communication applications, but more to develop the on-chip sensors, it is possible to think of a word and to give that scenario, I would like to leave with a teaser. So if you can imagine a phone clippable handheld optical device that you can just clip with your phone and then can help you sense and provide your safer indoors and outdoors, and of course a clean environment that we all definitely strive for. So, and if you have any more interest in knowing more about this work, we have some work that has already been published, but I'm also happy to answer the questions from now. Thank you so much for listening.
Robin, thank you so very much. If you have questions, please raise your digital hand, or you can type in the chat, and I will try to sequence the questions in the order that they come. Let's see. C. Antoine, I think, is the.
Hi, can you hear me?
Yeah.
Yes.
Hi, my name is Christophe Antoine from Analog Devices. I've got a question for you, Robin. So I'm curious if you looked at potential interferers. So I was interested when you showed your fingerprints, you had several resonators and you were showing that looking at different particle sizes, you could differentiate it because the patterns look different. Have you looked at interferers such as temperature, heat, any type of other gases that you were not planning on that would essentially give the same readout to your sensor and you wouldn't be able to deconvolve them?
Yeah, well, thanks so much. And that's a really good question. And in order to answer that, so about the first aspect of the interference from heat or any temperature changes, so we are using silicon nitride based photonics, which is very athermal. Like we tested some of our devices for different temperature, putting it on a thermostat, and we didn't see too much of variation, at least in the idea that in the range of temperature that we are working here. The other aspect where if we have other sort of interfering gases, definitely we can see the change, and that change would be very crucial in order when we want to back calculate the particle size. So in order to do so, like the way we are testing is we are sending these aerosol particles through vacuum phase, so trying to avoid any gas medium. But if we can have some a priori knowledge about, okay, these aerosol particles have this gas as background, or we want to use these sensors for very particular applications, we can recalibrate these sensors to take care of those kind of like applications and then deploy these sensors. Yeah, so that's the idea.
Thank you.
Yeah.
Robin, a question that came, so let's see, I have two questions here. Jelena Notaras, and then I had a private question that came in. So Jelena?
Hi, Robin, thanks for the question. This is Jelena. Question for the Chalco platform. Are those do you have integrated detectors in that platform, or is that detected off chip? How does that look? And I guess the platform is an in-house process. Talk a little bit more about that.
Yeah, sure. That's again a very good question. And so about the chalcogenide glass-based mid-IR photonics. So I've been very strongly collaborating with the Microphotonics Center, and we have shown, and there are already published work from our group, that we have the on-chip sensor module as well as on-chip detectors. So we have developed lead telluride-based detectors that could sense these optical signals and transduce them to the voltage output. And these all are developed in-house at MIT.nano facility, and as well as some of the customized evaporators and other deposition techniques that we have.
So thank you for that. Robin, a question that came to you on a private chat, how to purge the device. I interpret that to mean if the device has been exposed to something for a period of time, is it possible to clean it or to reuse it?
Yeah, that's again. So these were some of the experimentation issues that we were dealing with, and working with Peter. We realized that it's good if we were purging it with nitrogen after every measurement, and that purging, like how much you want to purge, could depend on what kind of aerosol medium you use. If you have more volatile aerosol medium, so we don't need to purge for too long. But if you have the gas or the solid particles, then it is important to purge it very heavily so that you don't have any base noise there. So definitely purging is one of the things that we need to take care here.
Let's see. Maziz, I think Maziz 3, I think had their hand raised. Maybe I missed that. Maybe that was okay. Another question that came on a private chat here. Long-term stability. Do we expect degradation of the underlying photonic device, and just in general, or when exposed to some of the chemicals? I think is the question.
Sure. Yeah. So I think that's a lot more dependent on the materials that we are using here for our photonic devices. Silicon nitride has been a lot more stable, so you can definitely expect a long-term usage of it. But for mid-IR photonics, where we're using chalcogenide glass-based materials, they definitely show some kind of degradation over a period of months. And then there's also research going on how to improve their lifetime, etc. But this would be more critical for the mid-IR photonics and less for silicon nitride-based photonics.
Let's see, any other, let's see. Here's a question from Jihan Kim. How are the optical filters implemented for the fluorescent detection biopic?
So if I could understand what optical filters are meant here, or
Jehan, are you able to go live?
Yes, thank you for a wonderful talk. So I think in conventional fluorescence detection, we have excitation filters and emission filters that are designed for the type of fluorophore we're using. I'm wondering if does a micro resonator serve this purpose of filtering out excitation, or is there some extra component that does this function?
Yeah, well, yeah, again, that's a very good question. And regarding, like, I'll answer it both from the detection point of view as well as from the excitation point of view. So we excite for a particular wavelength of our interest, like based on what kind of fluorophores we are using. So there, like, it's just a laser diode that has this very narrow band output, and we have the particular wavelength excitation. But for the detection part, we can implement our filters, like the wavelength filters, or based on the way we design our grating structure. So the meta grating structure could be designed so that it operates only at particular wavelength, and it doesn't couple in wavelength that are not of our interest. So that also helps us to serve as like a on-chip filter without having too many other components.
I see. Thank you.
Yeah.
Okay, Rob, another question that came in from AT. You can either ask it in person, or I'll read what you chatted here. How can we easily measure the Q factor of each cavity peak without using a bulk full-size spectrometer?
Yeah, so the measurements of the transmission spectrum that I showed you definitely has a broadband transmission spectrum, but I would imagine like there's been a lot of work individually on the light sources, on the detector part, and the sensor module parts. So I would imagine not using a bulk size spectrometer, but using wavelengths, like the discrete wavelengths, more sort of like the comb laser, and the detectors operating at particular wavelengths. And based on that, it is possible to like hit the wavelengths that are exactly at the quality factor and try to understand what's the relative change there.
Great, thank you. So I think we probably have time for one more question, and I see a question from Kieran. It said, great presentation. A question, are you planning to test your design in the immediate future to detect COVID-19 cases? Thank you.
Well, I will leave that to Brian. He has
Yeah, it's certainly there are some opportunities where there, as you've seen, there are some funding opportunities for novel sensors both in the short term and the long term, and Robin is taking the lead on writing a concept paper around how to do that. So certainly, I think it's something we want to explore. Okay, so I think with that, unless I missed a hand, let me just check. See, Anton, is your hand still raised, or did you have another question?
Yeah, I'm all good.
Okay, good. So, so thank you, everybody. If you would like to clap, there is a clap or a thumbs up on the ellipses to the bottom of the participants window. I wanted to thank Robin again, and also alert you to next week on Tuesday. Our Nano Exploration talk will be from Dahlia Klein on magnetism and the ultra-thin limit, and then on Thursday, April 9th, will be Praneeth Namburi talking about dance-inspired investigation of human movement. Robin, again, thank you for your excellent presentation, and everybody stay safe, stay well, and see you next Tuesday.
Thank you so much, Brian, and everyone for joining.